caso de alguna emergencia, que espero no ocurra, ¿verdad? Pero bueno, hay que estar preparados. Ya ven que todo puede ocurrir, ¿verdad? Entonces, cualquier cosa, cualquier emergencia, todo, hay que desalojar la sala de manera tranquila, en paz, sin gritar, sin aventar, sin patear, golpear, etcétera, etcétera, al otro, con calma, por las mismas puertas por las que entramos, que son estas, o también tenemos aquí otra salida de emergencia. Entonces, por favor, para evitar que la tragedia la hagamos nosotros, para evitar más accidentes de lo que ya en general la misma tragedia puede ocasionar. Bueno, entonces, a nombre del Departamento de Matemáticas y Física, muchas gracias por acompañarnos una vez más. Vamos a platicar hoy de un tema muy, muy interesante. Gerard Williger nos va a platicar de Quasars and Large Scale Structures. Estos quasars, estos instrumentos, estas estructuras, galaxias activas, muy, muy antiguas, muy, muy lejanas, ya nos dará los detalles Jerry acerca de todo esto. Y bueno, ya algunos tuvimos la suerte de vernos el día de ayer. De todas maneras, el día de hoy vuelvo a presentar a nuestro ponente que nos visita a la Universidad de Louisville, allá desde los Estados Unidos, ¿no? Ahorita tal vez les platique, ayer como estuvo platicando del Derby de Kentucky, del Bourbon, ¿no? Todo eso, bueno, pues ya nos platica. Es Kentucky Derby, sí. Entonces, bueno, pues una breve reseña de su extenso currículum. Él estudió, aquí lo tengo, permítanme, no es este, es este. Aquí está. Él estudió su doctorado en el Instituto de Astronomía allá en Cambridge, en el Reino Unido. Tiene su carrera, lo que sería para nosotros el Bachelor in Science, para nosotros nuestra carrera, tiene en astronomía, matemáticas y física, tiene 3 majors, 3 áreas importantes allá en la Universidad de Ohio, estudió la carrera, dentro de tantísimas cosas que ha hecho, bueno, pues ha sido profesor investigador y compañero de Fulbright allá en Budapest, Hungría. Ha sido profesor investigador y visitante en Lancashire, profesor visitante en Johns Hopkins University. Ha estado visitando los observatorios europeos del sur, European Southern Observatory, durante algunos meses. Ha estado en Cambridge University, ¿no? Con las becas de Isaac Newton y Marshall Scholarships. Es profesor asociado.
Professor complete. Oops, oh no, I'm not associate anymore. Oh well, that's okay. Oh, I see.
de tal cosas ya ni nos acordamos, ¿verdad? De todo lo que hemos. En Francia, ha estado en Francia, pertenece a la American Astronomical Society, European Astronomical Society, the Royal Astronomical Society, Kentucky Area Astronomical Society, etcétera, etcétera, etcétera. Bueno, Jerry, welcome.
Okay, gracias. Okay. Pregunté ayer, preguntar otra vez. Okay, tengamos una votación. Este es castellano, aprendí chileno, hacerlo todo. Y quiere la charla, okay, las diapositivas son en inglés. ¿Quiénes quieren la charla en castellano? Okay, ¿quiénes quieren la charla en and go there and have a talk once a month on astronomy. And you are pretty free how you do it, but it should be for the grand public. And so this is my challenge, and then you can discuss molecules in the sea of molecules. So today's talk is on quasars and large-scale structure. Quasars are a relatively recent discovery in astronomy. Astronomy is thousands of years old. They're discovered in the 1960s, actually. And it comes from quasi-stellar radio source, so something that looks like a star, but it's not a star. And I am interested in using them not to study themselves, they're very bright things, but what they do is they're lighthouses in space, faros. And so they're so distant, they are billions of light years or parsecs away, that the path of the light will go through many, many clouds of gas on the way to Earth. And thanks to spectroscopy and the expansion of the universe, that lets us map out where these clouds of gas are. And what are these clouds of gas? They're leftovers from the formation of galaxies, or they're galaxy halos, because galaxies are almost like living organisms. They take in gas from their neighborhood by gravity, or sometimes they smash together, they eat each other, or they also expel gas from star formation, supernovae, or winds from the central engines of these quasars. And so here we have a picture. Is this bright enough? This might not be working anymore. I might have too little electricity here. Here we have an observatory. Here we have the quasar. We have the light passing through various gas clouds. The light will be absorbed at certain wavelengths, depending on what gas it goes through. It's going to be hydrogen for the most part, but we also see other things like magnesium and calcium and silicon and so on. And then the light will make an absorption line at a certain wavelength. But because of the expansion of the universe, this quasar is going to be going away from us very fast. This one was going to be going away from us a little less fast, a little less fast, a little less fast. Even if we have hydrogen in all of these clouds, the hydrogen lines will be at different wavelengths because of the different speeds of recession or velocities of recession. So that means that we can make a map of the universe from things that we don't see because this gas is generally dark. You need something really bright to see it at a big distance, and the gas is dark. So what we're doing is we're mapping out shadows. So here are some pictures of some galaxies. We see gas. How many people came to the talk yesterday? Okay, I talked about molecules in space and formation of stars. Stars are formed from clouds of gas and dust. And so here we see some stars and some gas, and the gas is in clouds, and gravity pulls the gas together and eventually makes a star. That would be a story in itself. And this happens all throughout a galaxy. Here we have a picture of a galaxy like our own with 100 billion stars and a lot of gas. So here are a few types of galaxies. So this is our nearest neighbor in space, big neighbor. This is the Andromeda galaxy, which you can actually see with the naked eye if you look. It's up around October, and it will be a fuzzy patch, but you have to be away from city lights to see it. And it has some satellite galaxies, and you can see these dark streaks in it. That's dust. Galaxies have a lot of dust, and if you don't see stars, that doesn't mean there's nothing there. It just means that there may be some dust that's hiding the stars behind it. We have so spirals like this one, like the Andromeda galaxy. We have ellipticals, which can be round or elliptical, depending on how elliptical they are. And the spirals can be about the same size as the Milky Way, maybe 10 times smaller, 10 times bigger. Ellipticals can be easily 1,000 or 10,000 times smaller than the Milky Way, or 1,000 times bigger for the biggest ones. There's a huge variety. And then there are some irregulars. This is one of the Magellanic Clouds. I think it's the Small Magellanic Cloud. And they are basically just blobs. I mentioned that galaxies are almost like living organisms. They smash together. And then we see things like this. This is a Hubble Space Telescope picture of two galaxies that are merging. And so we have all sorts of things happening with galaxies. They also, like some types of living organisms, like to be together in groups. We call them clusters. And clusters can be very, very small. We actually live in something called a group called a local group with about 50 galaxies. But there are clusters with
thousands and thousands of galaxies as well. So here's a picture of one of them. There was a man named George Abel who mapped them out and found a lot of them in the 1950s. And this is a composite picture showing the galaxies in optical light. And then the purple shows where hot X-ray gas is, because the galaxies are surrounded by gas that you normally don't see, but when they're moving through the gas at big speeds, because they are moving at 1,000 kilometers per second here, it's just like taking a pot of water, ice water, and stirring it really hard. And that heats up the gas to 100 million Kelvin, and that is hot enough to give off X-rays. So we also see galaxies that are loners, just like certain types of living creatures, and they're called field galaxies. So we see a great variety in galaxies. Why am I giving you all this material in galaxies? Because quasars are in galaxies. So a little bit more about the galaxies first. For over a century, we have known that many of them are moving away from us. In the 19th century, there was a big advance in astronomy. Well, the first big advance in astronomy was the telescope, and Galileo used that. Who invented it is hard to say. We can ask Dr. Graney about that. But in the 19th century, we had photography. And photography allowed us to record images so that we could analyze them later, and we can make long exposure images. And we also developed spectroscopy in the 18th and 19th centuries, 17th, 18th, and 19th centuries. So we could take pictures of light going through a prism and record what elements were in some object giving off light. And that the spectra tell us how fast objects are moving, among other things. So this astronomer, Vesto Slipher, noticed that the Andromeda Galaxy was moving toward us, which is very unusual, at a pretty high speed, 300 kilometers per second. That's much faster than stars in our own galaxy go. And then what happened was people started to look at more and more galaxies and then realized that most of them were moving away from us rather than toward us. And we characterize this motion away from us by something we call the redshift. It's from the Doppler shift of light. Corrimiento hacia el rojo. Desplazamiento hacia el rojo. So what happens is this. Here's a spectrum of a galaxy which is at rest with us, and you see the different wavelengths and the different intensities of light. And then we see sometimes some spikes that are up. These are called emission lines, when electrons and atoms are jumping down in energy level. And we also see some absorption lines, which are from electrons jumping up in energy level. And each atom is like a tuning fork. It has certain frequencies and wavelengths associated with its electrons jumping up and down. As a matter of fact, not only each atom, each ion. So if you strip off an electron from an atom, then it has a completely different set of these frequencies. But that's good, because we can recognize them and identify what atoms are in an object. And then the Doppler shift will tell us how fast something is going away from us or toward us. So this is at rest with us, and this is moving away from us at about 1/10 of the speed of light, 30,000 kilometers per second. And you see that every wavelength is multiplied by a factor of 1.1. So we have the redshift, we add 1 to it, and then that's a factor of the light wavelength being increased. And this can actually be infinite. We see redshifts right now of 10 or 12. You can't equate the speed with the redshift so much anymore, because you have to start to worry about relativity. The maximum speed that something can go away from you is the speed of light. But if you have something going away from you at the speed of light, then the redshift will become infinite. But anyway, what this does is it lets us measure how fast the galaxy is moving away from us. And in our universe, 1/10 of the speed of light is nothing. Things can move a lot faster than that. So, in the 1920s, Edwin Hubble, who had the great fortune to work at the Mount Wilson Observatory with the biggest telescope in the world at the time, he was looking at galaxies, and he made a number of big discoveries. One of them was that galaxies, which were called spiral nebulae at the time, are very far away, because he found certain types of stars in them called Cepheid variables, and so he realized that the Andromeda Galaxy was very far away. The other was that he noticed that the farther away a galaxy was, the faster it tended to move away from us. And he published a paper in 1929 saying that the universe must be expanding because the farther away a galaxy is, the faster it's moving away from us. Now, 2 years earlier, a priest in Belgium named Father Georges Lemaitre, who was more of a mathematician, he didn't do his own observations, but he analyzed other people's observations. He published a paper in French, which also said the same thing: the universe must be expanding. Now, and I am speaking in English, I'm very conscious of this, there is an English bias even back then. And so, and Hubble even translated some of the paper, some of Lemaitre's paper. So today, we credit both of them with the discovery of the expanding universe, and they were both nominated for the Nobel Prize. Hubble died about 3 weeks before it was announced, and they don't give the Nobel Prize to people who have died. I don't know why Lemaitre didn't get it, because I think this discovery is one of the biggest ones in history, but certainly the International Astronomical Union credits both of them with the discovery of the expanding universe. Now, the expanding universe is important for many reasons. It means that there must have been a beginning time, and it also lets us map out where things are using spectroscopy and Doppler shifts. So here's a picture of, now let's switch to quasars. So there's a parallel story which begins much later. So in the 1950s, after World War II, radio astronomy really was starting to develop fast. It started in the 1930s, but with radar and World War II technology, radio telescopes became much bigger, and then there were big surveys in the sky. And in radio waves, we discover different things than in optical light. We can discover big gas clouds, for example. And we did realize that, for example, gas clouds, nebulae with hydrogen gas can give off radio waves with a 21 centimeter wavelength, and carbon monoxide and all sorts of other molecules give off radio waves. That's great. And then this object was discovered. So in Cambridge, England, which is where I did my graduate school, there was a telescope in a field which was used to map the sky. It was a very low-tech but effective way of mapping out radio waves in the sky. And there was a list of objects, and object number 273 turned out to be a point source. It looked like a star. Now, most stars do not give off many radio waves. A few do, but most of them do not. And so this was considered very strange. What's more, its spectrum was also considered very strange. Most stars have absorption lines in their spectra because they have a light-emitting area, and then they have an atmosphere on top of that, and the atmosphere absorbs certain wavelengths, and so we see dark lines in the spectrum of a star. Now, this is a negative. So actually, what's dark here is bright, and what's bright is dark. So this is a negative. And so this 3C273 has emission lines. That's very rare in a star, too. So this was a really weird object. Number one, it gave off radio waves. Number two, it had emission lines, which are rare. Number three, the emission lines were actually very broad. And that means either the temperature is high or it's rotating very fast. We don't know which. You have to work with it. So this is a picture of the spectrum here. And after a while, we were trying to figure out what kind of star was doing this. Martin Schmidt, who's still alive, he's an astronomer at Caltech, he's a Dutchman, he realized that 3C273 had an enormous redshift of 16%. That meant that it was moving away from us at 16% of the speed of light. This was unheard of. In our galaxy, stars move around relative to Earth at speeds of maybe 50 or 100 kilometers per second maximum. If they go 200 kilometers per second or 300 kilometers per second, they reach escape velocity and they will leave our galaxy. So we should not see stars traveling that fast. This was going at 16% of the speed of light. That's 48,000 kilometers per second. So this was absolutely unheard of, and higher redshift, more distant than any galaxy than we knew. So this was hard to accept that this point-like object, which was actually pretty bright, it's 13th magnitude. This is a about 600 times fainter than you can see with your eyes. And if you have a telescope with a diameter of about 15 to 20 centimeters, you can see this object with the naked eye if you have a nice dark sky. So this is bizarre, that this is this object which is traveling fast away from us, it's giving off radio waves, and its spectrum doesn't look like anything we know, and it looks like a star. And if the velocity comes from the expansion of the universe, it is farther away than any galaxy we knew at the time. So this is absolutely strange. If we look from the ground with what's called a direct image, a picture, we can do two things with a telescope. We can take a picture like this, or we can put the light through a grating or a prism and look at the spectrum, and then find out what elements are in it, how fast they're moving, what the temperature is, that sort of thing. We see a point, and then we see this little streak, and that's what we see from the ground. Here's another star. If we look at high resolution, this is with the Hubble Space Telescope, which was launched in 1990. This is from probably about the 1950s. We see the streak in better detail. It has some curves. It's like a corkscrew. These spikes are called diffraction spikes. They occur with every telescope that has a structure to hold its mirror, a secondary mirror in place. And then we see maybe something here. If we block the light from the center with a little artificial eclipse using a piece of metal, it's called a coronagraph, then we see a faint, fuzzy area around this object, which turns out to be a galaxy. It's an elliptical galaxy. So this strange object lives in the middle of this galaxy. And again, it's called Quasar 3C273 because it's the third Cambridge catalog, object number 273. Astronomers are not terribly imaginative or exciting with most of their names because we just have too many objects. So we call them telephone numbers or catalog numbers. So this is really weird because people were trying to figure out what is a quasar. What we think they are, after eliminating every other possibility we could think of, is they are gas spiraling around a black hole with a mass of anywhere from 1 million to 1 billion times the mass of our sun. And they're spiraling around like water going down a drain. And the gas is going faster and faster. Now, this is a disk, and it's a gas. So gas at one radius will not be traveling at the speed of gas at another radius. The closer the gas is, the faster it will be going, and there will be friction between the particles. I won't say atoms because it's so hot that the electrons are stripped off, so they're ions. And so you see something like this. Here's your black hole, and then around it is this disk of material which is spiraling in, and it's hot. And just like yesterday, if you saw the talk yesterday, when you have a disk of material spiraling into a central object, whether it's a star, a young star, or whether it is around a galaxy center, then the pressure and temperature get to be so high that some of the material gets squirted out the path of least resistance, which is the poles, and you get jets, which is what that and that are. They're material that's being squirted out from the accretion disk at the last minute. It's like you have a bathtub and you're trying to pour water down the drain and you pour down the water too fast and it splashes back. So this is the splashback. Now, hot gas will radiate light. We call it black body radiation or Planck radiation. And the hotter it is, the shorter the wavelength of most of the light. So the temperature here is going to be around 10 million Kelvin. And that's hot enough so that it gives off a lot of X-rays. But it gives off light of all wavelengths. All objects give off light of all wavelengths. We human beings have a temperature of about 300 Kelvin. Most, of the light that we give off is at about 10 microns in infrared light. The sun has a temperature of about 5,800 Kelvin. Most of the light that it gives off is in optical wavelengths. Our eyes see it as yellowish white, and That's what passes through our atmosphere. That's the light that we get. So our eyes have adapted to see mostly optical light. For 10 million Kelvin, it's X-rays. But still, there's a little bit of light that's optical, and that little bit of optical light is what we see here and here. So, the size of the accretion disk is not very big. The black hole is about the size of our solar system. Not very big at all. The rule of thumb for a black hole, for every solar mass, it has a radius of 3 kilometers. So if you were to take the sun, crush it down to 3 kilometers, it would turn into a black hole. We would keep orbiting around just the same because gravity doesn't care whether the sun is the sun or a black hole. If you have a million solar mass black hole, that's 3 million kilometers, that is about 1/15 of the size of the orbit of Mercury. If you have a billion solar mass black hole, that's 3 billion kilometers, and that's going to be about 20 astronomical units, which is the size of the radius of the orbit of Uranus for a billion solar, so about solar system size, something like that. Now, as the gas moves in, it's spiraling around faster and faster, it gets hotter and hotter, it emits X-rays. Now, there's another thing that happens with fast-moving ionized gas. So the gas is too hot for the atoms to keep their electrons. So the gas turns into what's called a plasma, which is the protons, and it's mostly hydrogen. The protons and the electrons are free. And you have moving electric charge. And so you generate magnetic fields. And by the way, the protons and the electrons have similar energies but different masses, and they're traveling at different speeds. So you've got this sea of slow-moving protons and fast-moving electrons. So your electrons are moving faster than your protons, and they're spiraling around. So we generate magnetic fields with this fast-moving ionized gas. And the magnetic fields are what is controlling the shape and direction of these jets coming out from the quasar. Now, how many quasars are there? We know of about 1 million, roughly, now. They were discovered in the 1960s. But there are many more galaxies. So in the local universe, we don't know of any. The closest one is the one that was discovered, the 3TC273, which is about, let's see, redshift of 0.15, so 30 to 45,000 kilometers per second. It's around something like 2 billion light years away, the distance of 3TC273. That's the closest one. All the other quasars are farther away. There are smaller versions of these quasars, which are called active galactic nuclei. They're lower level. If a quasar is a 100-watt light bulb, then an active galactic nucleus is, say, a 1-watt light bulb. So they're just fainter versions. Now, in the recent past, we have constructed groups of radio telescopes which work together, and they give us super-duper detailed vision. They're called interferometers. And actually, is there one by the Large Millimeter Telescope, an interferometer? Oh, that's cosmic ray. That's cosmic ray telescope. Yeah, but there's one called the Very Large Array. If you've seen the movie Contact, we can get lots of radio telescopes to work together. We have to do some fancy electronics and computing, and then we get the detailed vision of a telescope as big as the distance between the dishes. So what we did a few years ago was we took radio telescopes and millimeter telescopes all over Earth and used the entire Earth as our radio telescope array to get the best possible detail in an image. And so they looked at a quasar, well, an active galactic nucleus. They looked at a big black hole in the middle of a galaxy called Messier 87. It was discovered in the 18th century with the naked eye. It's that bright. And it's not a quasar, it's an active galactic nucleus, so it's a little bit less bright. But we have a picture of the black hole in the middle of a galaxy. And it turns out that we have black holes in the middle of most galaxies, just most of them are not very bright. And we'll see why. So the very bright quasars are 1% or 0.1% of galaxies, at least at a distance of 2 billion light years or more. So this is how it would look if you're going in toward the supermassive black hole in the middle of a galaxy. So we're going into the galaxy. We see the accretion disk, and then we see jets coming out of the accretion disk. We're not at the black hole yet. The black hole is very, very small. There's the accretion disk, sorry. And then you see the jets, and then this little thing here, which is going to be solar system sized, is where the black hole is the event horizon. So, for me, I don't do research on quasars. There are people who do. They want to figure out how does the accretion disk work, where does the gas come from. Gas comes from the host galaxy of a quasar. Sometimes galaxies crash into each other, and then a big galaxy eats the little one, and then absorbs the gas, and the gas gets thrown onto the black hole, and that's what makes it bright. I use quasars as lighthouses because I'm actually interested in these things, these puffs of gas around other galaxies. We can map out where they are, and we can determine the conditions in these galaxy halos, the density of the gas, the temperature of the gas, what elements are in them, and so on, because they give us a clue about the formation of galaxies. It's like looking at the garbage dump beside a city. Or you're looking at the farmland around a city, depending on if the gas is going in or the gas is coming out. And again, 3C273 is 2 billion light years away. Most quasars are farther away than that. The farthest we can see, by the way, it's called our horizon distance, is 13 billion years, 13.7, because that's how old we think the universe is. And so light can only travel for the time of the universe. So we might not see all of our universe, but that's what we can see. That's our horizon. So we're talking about billions of light years away. So let's go back to galaxies a bit. So here you have a galaxy. This is a spiral galaxy, so it has spiral arms. It has what we call a disk, and then it has a bulge in the middle. And it has patches of gas in it where the stars are forming. That's basically what's in the galaxy. If you look in detail at the halo around a galaxy, this is our Milky Way. So getting a picture of our Milky Way is very hard because we live inside of it. It's like going to a maze or a forest, and it's one thing to look at the forest from the outside or from an airplane or a drone. If you're in the middle of the forest, it's actually very hard to figure out what its shape is or where the patches of trees are and where the empty spots are. So this is our best estimate. Here's the disk of our galaxy. There are some patches with dust where we don't see so many stars. And then this is mapping out the gas using radio and microwave telescopes. And we see an incredibly complicated network of gas clouds. We see our two Magellanic Clouds, our satellite galaxies, which are just at the horizon here, I think. You have to go farther south to see them. And if you ever have a chance to go to the southern hemisphere, the sky is absolutely beautiful. Has anybody here been to the southern hemisphere? If you have a chance, go, because 22 out of the 25 brightest stars in the sky are visible from the southern hemisphere, plus the galactic center, plus the Magellanic Clouds. They're all fantastic. Even if you get to, say, Venezuela, you probably can see these things. So anyway, we have this network of gas clouds. So the Magellanic Clouds have some gas. They're orbiting around our galaxy, and they are trailing gas, because every time they pass through our galaxy, the gravity from our galaxy pulls out some of the gas. So it's like a trail left from a snail, from a caracol. And we also see other patches of gas that we think are falling in or coming out, because we have supernovae exploding in our galaxy, and they're pushing the gas out, rises up, and then it falls back down, because the galaxy's gravity pulls not just into the here, but the disk pulls toward the disk. The material in the disk pulls material down. So the gravitational field for our galaxy is actually complex. So we have these gas clouds. Now, if we look at a bright object far outside of our galaxy, the light will pass through all of these gas clouds, and the absorption lines from the gas will be superimposed one on top of the other. Now, if we're looking at a bunch of galaxies and they're far apart and they're expanding away from us at different speeds, then the Doppler shift will separate out the absorption lines. But for our galaxy, the speeds of these clouds are low. They're in orbit around our galaxy. They're a couple of 100 kilometers per second. So all of the absorption lines are mixed up with each other. And so our job is to try to unmix them to figure out what's the density and temperature and what elements are in each of these gas clouds, because they're different. If a gas cloud has a lot of heavy elements like carbon, nitrogen, oxygen, magnesium, then the gas was cycled through many generations of stars. Stars make heavy elements, anything other than hydrogen and helium. So if you have a lot of heavy elements, that means that the gas went through a lot of stars. If there are not many heavy elements, then the gas did not go through a number of generations of stars, and that gives us an idea of what was the history of forming stars in various parts of our galaxy. Or, if we look at another galaxy, what's the history of making stars in other galaxies? And that's why we're cosmic forensic scientists. It's like doing an autopsy on a dead body. How did this come about? Or our cosmic archaeologists may be better. So, back to a spectrum where we have wavelength and we have intensity of brightness. This is looking at a distant object, our same quasar friend, 3C273, and we can look, here's some gas from our own galaxy here, and then we see some other dips. These are from, some of them are from our own Milky Way, and some of them are from gas between us and 3C273, which is 2 billion light years away. Which is which? That's our job to find out. You can use some clues. For example, there are certain elements which have lines which occur in pairs with a known wavelength difference. And we can use those as a fingerprint. So things like magnesium, singly ionized magnesium, that has a very characteristic pattern of absorption lines. So we can identify that. And carbon, triply ionized carbon, that too. If we don't know what something is, it's often hydrogen. So we can map out where the material is by its redshift. If it's redshifted, then we know that it comes from outside of our galaxy. If it's got a high velocity away from us. And if it's got a very low velocity away from us, it probably comes from our own galaxy. It's like looking at other forests from the inside of our own forest. It gets hard. So we call these dips quasar absorption lines because this is the light from the quasar. It has a giant emission line. This is from hydrogen. This is from hydrogen. And it has a bunch of absorption lines. So the quasar absorption lines let us be cosmic archaeologists and dig through the various levels of time in our universe. Now here's a picture of a galaxy with some neighbors. Now the problem with astronomy is that when you take a picture, you don't know how far away things are. You have to work pretty hard to figure out how far away a star is or how far away a galaxy is. You can do it, but you have to put telescope time in, you have to take spectra, and so on. So here you have galaxies of a bunch of different redshifts. Here's one with a quasar. This is our distant target. And then there are some galaxies actually in the foreground. So this is at a redshift of 0.28, 0.27, 0.17. The quasar, I don't even know what the redshift is behind. Oh, quasar, yeah, the quasar is behind. So it's redshift of maybe 0.3. And so what, this is my collaborator and friend actually, Joe Roboto, he looked at spectra of this quasar and tried to map out where the absorption lines were here. And these are all, for example, from hydrogen at different distances and different redshifts. And so sometimes they're the same. Actually, these are, oh, come to think of it, these are all from the same redshift. These are different hydrogen lines. It's called the Lyman series. So it depends on which electron jumps are happening. So we have a lot of absorption lines to identify, but we can work it out. And this particular spectrum was taken with a space telescope because it can observe wavelengths that we cannot observe from the ground, for example, in the ultraviolet. So, jumping back to galaxies and also quasars, in the 1980s, we started to make big surveys looking at as many quasar redshifts as possible and making maps where the quasars are in the sky and at what distance. And what we did was we went along a line in the sky and then made a plot of right ascension is basically like east-west in the sky, and then this is distance. So these are like pizza slices in the sky to show us where the galaxies are And by the way, the quasars also are out there. And what we see is that there are regions with lots and lots of galaxies. This is called the Great Wall. And then there are regions with fewer galaxies. They're called voids. And so the structure of our universe on scales of billions of light years is like a sponge. We have places of high concentration and places of low concentration. And the areas of low concentration, the voids, tend to be connected like tunnels. And the areas of high concentration, they tend to form when you have sheets of galaxies intersect each other. We have sheets, which are two-dimensional structures of galaxies. We have filaments, which are, say, where two sheets intersect. And then nodes, which is maybe where three sheets intersect. So we have this incredibly complex structure of where are the galaxies. You can think of foam or bubbles. And we see something like this in simulations as well. So here's a node, a sheet, and a filament. And we put together computer programs to set up some initial conditions based on our best estimates of how we think the universe formed. We put in some random density fluctuations, some dense spots here, less dense spots there. And then we turn on gravity and let it go. And we end up with something like this. And this is exactly what we see here. Now, the details are tough. We try to do statistics on the simulations and statistics on the observations to make sure that we actually have the right, what are called initial conditions, and that we have the right physics going on, too. Come on. There we go. So here is, let's see if I can get this to go. Here's a simulation of gas and what we call dark matter, which is not gas. And we're looking at redshift here. As the redshift goes down, time goes up, because redshift is associated with a time in the past, in billions of years. And you can see, actually, that the gas and the dark matter are flowing toward dense regions. The rich regions get richer, and the poor regions get poorer. And what we get in the end is these clumps of gas and then dark matter, which is the subject of another talk in itself. We don't know what it is, but we know that it pulls on things. We can see the effect of its gravity. And we end up with this bubbly structure yet again. So I showed you a picture of galaxies, a galaxy survey. This is galaxies out to a redshift of about 0.2. 3C273 there are no quasars closer than this distance. These are all galaxies. The problem is galaxies get faint if you look at them very far away. Quasars are very bright, so we can map them out to great distance. So this is a map of, well, I guess this is still galaxies. The quasars are going to be out here. I should have a quasar slide here, too. And they should continue to show us the structure, because about 1% or 0.1% of galaxies have quasars in them. So we can use them to map out galaxies where galaxies themselves are too faint to see, because quasars are so much brighter. The quasar is the bright core of a galaxy powered by a black hole with gas spiraling down it. And a quasar shines brighter than its host galaxy by a lot. So we can map out quasars, and we can also map out the shadows in front of quasars, because those tell us where galaxies are too, and we don't have to see the galaxy. So if the quasars are out here, we'll see the galaxy shadows, we'll see absorption lines from galaxy halos out here beyond the point where we can see galaxies shine from their own light. So they're really, really useful to help us make maps of the distant universe. So this is a collaboration that I'm involved with. I've been working with Roger Claus and also Luis Campuzano from Universidad de Chile in Santiago for a number of years. And they work with things called large quasar groups. So our galaxy, just to give you an idea of scale, so we have our sun, we have our solar system. The nearest star is a few light years away. The middle of our galaxy is about 30,000 light years away. The next galaxy, the next big one, the Andromeda Galaxy, is 2 million light years away. And galaxy clusters, actually, where you have potentially thousands of galaxies, will be maybe a few million light years across. That's it. Now, quasars are very bright and very rare, and they appear to form collections. I don't want to say clusters, collections, which could be 1 billion light years across. They're rare, but they're very bright. Now, there's a crossover point. We call something a cluster if the objects inside of it are held together by gravity. There's a size above which a system of objects cannot exchange energy by passing through the middle of this group enough times in the history of the universe. So it's a maximum size to a cluster to be held together by gravity. And it is some millions of light years in general. It depends on the amount of matter in it, and it depends on the size. So this large quasar group, which is shaped like a fish hook, is too big to be held together by gravity because the distance is too big for objects to cross from one side or the other in the age of the universe. But it's there. It's statistically significant. So what is it? And our best explanation, well, there are two explanations. One is chance. But we see dozens and dozens of these groups, these large quasar groups. The other thing is it could be a leftover from big, dense areas that arose soon after the Big Bang. We call them quantum fluctuations. So what we see here is this large quasar group, some billions of, a couple billion light years across, and it's a redshift of 1.27, so its distance is about 8.5 billion light years, so 4 times farther away than 3C273. And the age of the universe at this point was only about 5 billion years. The universe was 1/3 of its age when we see the light from this group coming across. And you see, by the way, the constellation of Leo the Lion in comparison, and this is the size of the full moon. So this is really big on the sky, if you could see it. So these are called large-scale structures or giant structures. And so they are maybe 10 degrees across. 10 degrees on the sky is your fist at arm's length. Normally you look at a star and it's a point. Look at a galaxy, it's a little thing on the sky. These structures are big. If you could see them, they would stretch out many times bigger than the full moon. So the biggest large quasar group that we see is about 30 degrees across. That's 1/3 of the distance from the zenith to the horizon. That's really, really big. And of course, they're so big, there are not very many of them, but we see them. So, a group that I was working with Roger Klaus and his student Alexia Lopez, found by chance a big collection of objects, not of quasars, but of the absorption lines, because we map out the absorption lines toward quasars. And we know how far away they are from their Doppler shifts and the expansion of the universe and the Hubble-Lemaitre law. And it covered that we used what's called the Sloan Digital Sky Survey, which was made here at Apache Point Observatory in New Mexico. It's worth a visit if you can drive up there. And so about 20% of the sky was mapped with deep images and with galaxy spectra and quasar spectra. And in the quasar spectra, Alexia found, there's a catalog, people made the catalogs, she looked in the catalog and found this group of objects which appear to be together in the sky at the same distance, covering something like 10 or 20 degrees, something like that. And she was looking at spectra like this, or looking in the catalogs, where people were looking at spectra, or machines were looking at spectra, to find magnesium, singly ionized magnesium, which makes a double line like this. And there are some other lines from ionized iron and so on. And so what we're doing is we're looking at quasars, we're looking at the absorption from galaxy halos around them with this telescope here in New Mexico. So this is a map in 2 dimensions of what Alexia found. The gray areas are not single absorbers, they're groups of absorbers with high density regions. And it's 18 degrees across, so that's about 2 fists at arm's length. That's really big on the sky when most of the time you're looking at stars which are just points. And what she found was this. And to your eye, okay, the human eye is very good at picking out patterns, whether they're there or not. She looked at this and said, that really looks unusual, because she looked through all of the data many, many times. And then the challenge was to look at the statistics and determine, is this by chance or is it real? And we're talking about 1,000 megaparsecs. It's about 3 billion light years from one side to the other. So here's the giant arc on the sky. Here's some constellations you can see from here. Here's Corona Borealis, which is quite bright. Here's Boötes. Arcturus is down here. That's a very bright star. And it stretches from Boötes over to, this is a faint constellation, Canis Venatici. It's big on the sky if you could see it. It's just very faint. The quasars are probably going to be about 18th to 20th magnitude. We're talking about 1 million times fainter than your eye can see, roughly speaking. So how do we test whether this is real or is it by chance? We have to use statistics. We look at the distribution of the probability of finding these magnesium-2, the singly ionized magnesium absorbers, and the test in science is usually you want to find something which is very, very unlikely to happen. You go 1 standard deviation, 2 standard deviations, 3 standard deviations away from what's called the bell curve. If you have 4 to 5 standard deviations away, then the chance of something happening randomly is much less than 1%. That's what we scientists like to say is a solid detection of something is different. So we used a few tests on randomized data to determine, is what we see significant or not significant? And so we use something called the minimal spanning tree, which is basically connecting dots with lines, and then looking at the lengths added up of collections of lines. And we see that with what's called the minimal spanning tree, we find about a 4 sigma significance. So the chance is less than 1% that this giant arc here arose by chance. Less than 1%. And so we did another test which was adapted from archaeology, from looking at, and also from public health. You can test in a place and say, is there something there or not? But you only know where you test. So it's like drilling holes in an archaeological dig or getting statistics from public health associations. So for example, here is Michigan. There's a big city here. There's a smaller city here, and then there are smaller towns here. You're looking at instances of, in this case, breast cancer. Is it clustered in some places or not? We use the same test statistically to find out, do we have magnesium-2 absorbers here preferentially or not? These are the singly ionized magnesium. And so we did a lot of tests. We shuffled the data, and we found out it's about 0.7% chance of having something this big be connected in our data. And so that's roughly about 3 standard deviations, which is worth publishing. It's not as good as 4 or 5 sigma, but it's pretty good. And we actually got this published. We also did a third test using something like Fourier analysis, looking at collections of pairs and triples and so on. And again, we got a probability of less than 1% at nearly 5 sigma. So we tried 3 different tests. Each test gave us a probability of 1% or less than 1%, and each test was independent, very different from the others. And so what does it mean that we have this big thing that's very unlikely to find over 3 billion light years or more? It's too big to have grown by gravity. It's left over from the Big Bang. Somehow, probably. Now, there is a principle called the cosmological principle, which says that every bit of the universe should be like every other bit of the universe. There should be no unique places in the universe. This is unusual. Does it violate the cosmological principle? Maybe not, because you expect a few high-density regions. But if there are a lot more of these regions which are too big to pull themselves together by gravity, that would be a challenge. There are other teams working on these large structures, and they're also finding a few of them. The trouble is they're so rare, there are only a few in the sky. So doing a statistical analysis is very hard. We're working on another object called, it's just basically a circle which is nearby, and it's it's about the same size. So this is it for quasars and large-scale structures. I hope you enjoyed hearing about the big black holes and the vacuum cleaners and bright galactic cores, and I'm happy to take your questions. ¿Preguntas?
Por favor, si tienen preguntas, las podemos hacer vía el micrófono para que queden grabadas. I've got a question, and then Juan Carlos. Why do you think this apply as well for the galaxies? This kind of arrangement and this kind of behavior? And have you got any good, not the answer on, I know, but maybe a clue or evidence, or do you suspect about why the galaxies and the quasars have this kind of arrangement?
Well, there are things called initial density perturbations in the early universe. The whole universe was a hot, dense place. It's just like in the song about the Big Bang Theory. But the hot, dense place was not completely uniform. There was a mechanism to smooth out the universe when it was hot enough and dense enough. We say that light and matter were coupled. But when the universe was expanding and getting cooler, when it got cool enough for electrons and protons to come together, suddenly the universe became transparent and light was no longer trapped by dense regions of gas. And so whatever dense regions were existing at the time of this decoupling, or it's called recombination, it's about 300,000 years after the Big Bang, whatever dense regions were there stayed dense. And they persisted. So we think that this could be a leftover of that. And in the universe, you expect statistically there's some dense regions and less dense regions. These could be quantum fluctuations left over from the early universe. That's what I think is the best explanation. Now, there are a number of scientists who say there's nothing there. It's all by chance. We expect this to happen. You found nothing important. It's possible. The trouble is that what we find is so rare, it's hard to get a good collection of objects. The Sloan Digital Sky Survey looked at 20% of the sky. There's a survey coming up with the Large Synoptic Survey Telescope in Chile. It's being built and it's getting first light soon, which will survey the southern sky in a similar way, at least with images. There's another survey with a satellite called Euclid, which was launched last December, I think. And so it's going to survey about 40% of the sky as well. It's in orbit, so it can look in the southern hemisphere. So in the 2020s, this is the age of big surveys, we will get other samples independent of the Sloan survey and find out if there are objects like this. Now, the amount of telescope time, it was years and years and years of telescope time to get the spectra. Getting images is easy. We will eventually map out more of the sky and find out whether these are real or just statistical fluctuations.
Well, my question is about what does the light emission of these quasars do to its own galaxy or to its near surrounding galaxies? For example, talking about nebula or atmospheres of stars or planets.
Okay, let's go back to, I have to keep turning this off and on because the batteries are weak. Let's go back to the picture of how a quasar is built. Here, all right. So there's this accretion around this black hole. Okay, here it's 10 million Kelvin. So the gas is too hot to hold on to its electrons. The emission lines come from hydrogen, which is not ionized. So this goes out a long way. This will go out 30,000 light years easily, 10,000, 20,000 light years. So eventually, at a far enough distance, the hydrogen gas will hold on to its electrons, and it's spiraling around the black hole. Actually, it's not going to be 30,000 light years. We can see the neutral hydrogen emitting light because the light comes out from the accretion disk, excites the electrons in the hydrogen, then they come back down and it emits certain wavelengths like Lyman alpha. And so, where's the spectrum? Here. These broad emission lines come from rotation. If it was temperature, the temperature would be too high for the atoms to hold onto their electrons. It's rotation, and the speeds are something like 1,000, 1,500 kilometers per second. For comparison, our sun goes around our galaxy at 200 kilometers per second. So this is 10 times faster than the sun orbits. And it's pretty close in. This comes from a region, we can map it out with spectroscopy. Where does this light come from? And it's very close to the middle of a galaxy. So by Kepler's laws, we can work out what mass is needed to pull the gas hard enough to make it rotate this fast to produce a spectral line this wide. And so that's how we know what's going on. So it's the neutral gas far enough away from the black hole, so it's not ionized, but it's still moving around really fast.
Have you got another question?
I just wanted to know if there's like a relationship between the quasars and dark matter. Like, one depends of other, maybe, or
not direct. No. Okay. The quasar is the bright nucleus of a galaxy, and the light comes from regular matter, hydrogen gas, that's swirling around and it's hot. Now, it's pulled by some big mass, 1 million to 1 billion solar mass. We have one of those in our own galaxy as well, but it doesn't have gas spiraling around it so much, so it's not bright. In the past, we probably had one of these quasars in the middle of our galaxy, but we wouldn't want that now because it gives off so many X-rays and so much ultraviolet light that if we had a quasar in the middle of our galaxy, we'd be dead. So we don't want that. In the past, we had one, in the distant past, and actually if a galaxy were to smash into our Milky Way and dump a bunch of gas on the black hole in the middle of our galaxy, it would get bright and might, at least in the neighborhood, it might not be so good. We're about 30,000 light years away, so we're at a reasonably safe distance, but that makes problems. For example, if you want habitable planets close to the middle of our galaxy, how do they withstand all of the radiation? Now, where does the mass come from? We don't know what dark matter is, but we know that there's about 10 times as much dark matter as regular matter. It's distributed in a galaxy in the halo, actually. Some dark matter may be absorbed by black holes, but we don't know, because once something goes into a black hole, you know nothing more about it. It's just matter. You have a kilogram of matter. What it was, we have no idea. So I can say that galaxies have dark matter in them, and quasars are in galaxies, and so quasars are surrounded by dark matter halos, what are called dark matter halos. So the dark matter can help pull matter in from other galaxies to feed the quasar and to make the black hole grow. But whether there's dark matter in the black holes, maybe some. We don't know.
Thanks.
Thanks. Can you explain more in detail about the quantum fluctuations and like the relationship between the Big Bang and...
Yeah, okay. This is not my field of expertise, but when we make initial conditions for our simulations, we cannot have something that's perfectly smooth. Because if there's something that's perfectly smooth and uniform density, there'll be no pull of gravity inside of that box anywhere. So we have to start it out. You can imagine density as being an analog to waves on the ocean. You'll have some regions that are a little bit higher and a little bit lower. But on our oceans, the water will tend to flow out and the waves tend to flatten unless there's something that's making them get big. Now, with matter, first of all, you're working in 3 dimensions, not 2. And second of all, gravity is a one-way force. So if you have a region that's a little bit denser than the surrounding area, it will pull and it will get denser and denser and denser. So these quantum fluctuations, quantum would be by chance. In quantum mechanics, you have chance things happening. Quantum mechanics is all about probabilities and chance. So there will be regions which are a little bit denser just by chance. What is the distribution of sizes and densities of these dense regions? We have some predictions based on quantum mechanics, basically. And then we try to put these predictions into practice by taking our box of simulation and saying we're going to have this many fluctuations which are 10 times average density, and this many that are 5 times average density, and this many that are 2 times average density. And of course, the big overdense regions are going to be rare, and the little overdense regions are going to be common, and then you spread them out, and then you turn on gravity and see what happens. So that's what we do with the quantum fluctuations. Where they come from, it's a statistical prediction from quantum mechanics. It's the same thing as, can you predict van der Waals forces? They exist and we can measure them. Can you predict where they are? No. Do you know they're there? Yes. Do you know how many of these regions are going to be? Yeah, you can characterize the behavior of a molecule moving around, but you can't tell in advance what it is. So what we have to do is make lots and lots of simulations and then see what happens.
And when something enters into a black hole, there's a probability that it becomes the strings from the quasar. O sea, that's like something, the poop. O sea, the thing enters and get out like that string from gas.
Well, when something goes in, it doesn't come out. The whole point about quasars is we don't see anything from within the event horizon. We see hot gas around it, and light can escape from that. And actually, the gas is a comfortable enough distance away, so we don't have to worry about something called gravitational redshift as well. So what we see is hot gas that's just being pulled very hard. And anything going in shouldn't come out. Now, black holes can evaporate, but it takes a long time. And it's again due to quantum fluctuations and pair production. It's called Hawking radiation. It'll take many times the age of the universe for black holes to evaporate, though. So once things go in, don't worry about them. Don't go into a black hole, by the way. You won't come out.
Well, actually, I have 2 questions. The first one is in the image of the
3C273,
first image of the quasar.
Mm-hmm.
You see that the quasar is very, very big in comparison to the host galaxy.
Well, this is just the light. Yeah, the quasar, the black hole is the size of the solar system. The galaxy is 100,000 light years across if it's like ours.
Yeah. So how did the astronomers discover that?
Well, what we did, man, I can't show this to you fast because it's not on my USB stick. We can take, let's see. We can take the way we take a spectrum of a galaxy. Let's see if I find a picture of a galaxy here. Yeah, okay. So here's a galaxy. When we take a spectrum of an object, we look through a narrow hole called a slit. And so we do that because the grating or prism will spread out the light in one direction. And so if you have a big round hole you're looking through, you'll get a smeared out image of that hole along a line. And so to get the sharpest detail possible, we look through a hole which is very narrow in one direction, but it can be long in the other. And so what we did with the space telescope, which has the sharpest vision we can have in optical light, is we would put the slit like this on the galaxy. And then each piece of the galaxy would show a Doppler shift, which way it's rotating. So this is how we tell in what direction galaxies rotate and how fast. And we can map out the speed of rotation versus the distance from the middle. And that will tell us, using Kepler's laws, Kepler's third law, how much material, how much matter, how many kilograms of matter is inside of that radius. And so with the space telescope, we can get in so close that we can work out the speeds are very high, and they're very close to the middle of the galaxy, that there must be 1 billion solar masses within some very small distance. And the only thing that it can be is a black hole.
Thank you very much. And the second question is, how do these discoveries, I don't know if that's the word.
Discoveries, yeah.
Yeah, discovering, how do they help better life here on Earth?
Ah, yes. Okay, astronomy is a basic science. There is nothing that we observe today that will help life tomorrow unless it's a comet that's going to kill us. By the way, has anybody seen Don't Look Up? Okay. Don't Look Up is a parody, it's a spoof, but they got one thing very correct. They took an average astronomer and cast Leonardo DiCaprio as the average astronomer. And as an average astronomer, that is a perfect casting to show what an average astronomer is like. Leonardo DiCaprio, think of that. Otherwise, if we're not going to discover a comet that's going to hit us in a few months, we won't change your life. But in history, the discoveries made long ago eventually do get used. So GPS is from relativity. Navigation, a lot of navigation, early navigation, mapping was using astronomy. For example, determining the size of the solar system. So it's a basic science, but all basic research eventually gets applied. There are mathematicians who do research on very strange systems of objects. They call groups and sets and so on. Well, guess what? When we invented computers, then the groups that mathematicians studied, just for the sake of studying them, suddenly became relevant in programming. So all research is eventually applied, but it might not be applied anytime soon. Now, applied research is, how will I make this corn plant grow taller? Tell me by next year, or you're fired. That's applied research. Or I'll give you $1 million if you can develop a better breed of cow. But basic research is, go and study this for the sake of advancing knowledge for humanity, and then you can think of it as having a good symphony orchestra or having a good art gallery. But eventually, basic research does get applied. You just don't know what it's going to be.
Thanks.
Anyone else? Okay, well, thank you, Jerry, very much.
Okay, el placer es mío. Vengan a las 4.
Well, I want to give Jerry this kind of certificate in the name of Mathematics and Physics Department and ITESO. Thank you very much,
Thank you very much.
Jerry, for your collaboration on this. And I want to tell you, please, well, say thank you very much for coming. And please, today at 4 at the Agora, the library, there will be Chris Greeny talking about the Jesuit astronomers, the new telescope, and the moon. That will be a very nice talk. It will be more informal. You can, well, the talk will be questions and answers, and it will be very nice to be there. So please, I invite you to be with Chris today. And at 6 p.m. in this auditorium as well will be Alejandro Márquez Lugo con Astrofísica de un planeta habitado. It's a subject right now. It's a very popular subject, so you ought to come if you like these kind of subjects. Okay. Tomorrow we will have these choques de vientos estelares vistos con el telescopio espacial James Webb de Joel Sánchez Bermúdez. He's coming from the UNAM. And the afternoon, I will be here. Thank you if you come. La supernova de Kepler y la estrella de Belén de la astronomía china a los evangelios apócrifos. It will be related. This talk will be about how this supernova, the explosions you see in the sky, change our models of how we see the universe, the models of the cosmology models, etc. It will be interesting as well. And the last one, habitabilidad en sistemas planetarios, buscando vida en otros planetas, de Leticia Carigui. He's coming from the UNAM as well. With that lecture, we will close the Semana de la Astronomía. But tomorrow, we will have two more small talks in the library. One from Jerry, the Great North American Eclipse of 2024. He is an ambassador, no, from NASA, the eclipse ambassador from NASA. So you can ask and talk with Jerry about the eclipse and how to see it, no? Like the talk we had in Monday afternoon. And again, Chris Greeny will talk the Jesuit astronomers, the new telescope, and Jupiter, how these moons, the Galilean moons, the discovered by Galileo of these moons, how the Jesuits collaborate and they check out how was this discovery made by Galileo. So if you like this subject about the history, you will be very glad to be there talking with Chris. He's an expert in these matters. Okay? Any question? Everything? Thank you very much for coming, and I hope to see you soon, okay, in the next talking. Thank you.
Remember, Leonardo DiCaprio is a typical average astronomer portrayal.
Yes, of course.
We're all like him.
Yes, yes. Very simple.